This tutorial explains the kinetic molecular theory and how it relates to the ideal gas laws. So let's take a minute to review what we've learned so far. Properties of the gases. They expand to fill their entire container, and they take the shape of their container. They have very low density, much less than a solid or a liquid state. They're compressible, that you can compact them. The mixtures of gases are always homogeneous, and they're fluid, meaning that they can move around. The ideal gas laws can explain many of these properties. The kinetic molecular theory is the particles of the gases, either atoms or molecules, are constantly moving. The attraction between these particles are negligible, so in other words, they're going to spread out still. They're not really going to realize each other in existence. When the moving gas particles hit another gas particle or the container, they do not stick to each other. Instead, they bounce off and continue moving in another direction, like billiard balls. There's a lot of empty space between the gas particles, especially if you compare them to the size of the particles themselves. So if you look at all this room in comparison to this little itty-bitty molecule, there's a lot of space. The average kinetic energy of the gas particles is directly proportional to the Kelvin temperature. As you raise the temperature, the speed of the particles increase. But don't be fooled by thinking that all the gas particles are moving at the exact same speed. They're moving at different speeds, they're just averaging together. Because the gas particles are constantly moving, they strike the sides of the container with a force. The result of many particles in a gas sample exerting forces on the surfaces around them is a constant pressure, and we've learned this in previous sections. Because the gas molecules have enough kinetic energy to overcome attractions, they keep moving around spreading out until they fill the entire container. As a result, gases take the shape of and the volume of the container they are in. However, because there is a lot of unoccupied space, all this space in here, the gas molecules can be squeezed closer together. Because there's a lot of unoccupied space in the structure of the gases do not have to have a lot of mass in a given volume, which, as you may remember, is a definition of density. As a result, they have a low density, especially in comparison to a solid or a liquid. The pressure is the result of the constant movement of gas molecules and their collisions with the surfaces around them. When more molecules are added, more molecules hit the container at one instant, resulting in a higher pressure, also a higher density. Boyles laws state that the volume of a gas is inversely proportionate to the pressure. Decreasing the volume forces the molecules into a smaller space, meaning that they'll hit the sides of the walls more often. More molecules will collide with the container at any one instant, increasing the pressure. Let's take a look at Charles's law. Charles's law states that the volume of a gas is directly proportional to the temperature. So as the temperature goes down, the volume will go down. Increasing the temperature increases their average speed, causing to hit the wall harder and more frequently on average. In order to keep the pressure constant, the volume must then increase, and vice versa. Avogadro's law. It states that the volume of a gas is directly proportional to the number of gas molecules. Increasing the number of gas molecules causes more of them to hit the wall at the same time. In order to keep the pressure constant, the volume must then increase. And finally, Daltons Law of partial pressures. Daltons Law states that the total pressure of a mixture of gases is the sum of the partial pressures. Kinetic molecular theory says that the gas molecules are negligibly small and don't interact. Therefore, the molecules behave independently of each other, each gas contributing its own collisions to the container with the same average kinetic energy. Since the average kinetic energy is the same, the total pressure of the collisions is the same. So let's take a look at this even further. Since the gas molecules are not sticking together, each gas molecule contributes its own force to the total force of the side. Average kinetic energy of the gas molecules depends on the average mass and velocity, which this is actually a physics-related equation. Let's keep in mind these units, because those units are going to become important later on. Gases in the same container have the same temperature, therefore they have the same kinetic energy. If they have different masses, the only way for them to have the same kinetic energy is to have different velocities, different speeds. The lighter particles will have a faster average velocity than the more massive particles. Think of it as a difference between a bowling ball and a golf ball. It's a lot easier to make a golf ball go very far, 50 feet or whatever, in comparison to a bowling ball which barely goes down a lane, a bowling lane, and it's rolling. It's much harder to move. So it's going to be moving slower. All the gas molecules in a sample can travel at different speeds. However, the distribution follows a pattern called the Boltzmann distribution. And here's a graph. We'll get to a graph of it later. We talk about the average velocity of the molecules, but there's different ways to take this kind of average. The method of choice for our average velocity is called the root mean square method, where the RMS, average velocity, is the square root of the average of the sum of the squares of all the molecule velocities. And it's actually far easier to calculate than it sounds. So here's the Boltzmann distribution. So we have the peak here. This is where the most of them will actually have the speed. However, some of them are going to be moving slower, some of them will be moving faster, and it's all going to average out to be the same. Alright, so let's look at this equation. The kinetic energy, the average kinetic energy, is 1/2 of the Avogadro's number times the mass and the velocity squared. This actually then can be related to 1.5 RT. However, in our previous examples were 0.08206 atmospheres, liters, moles, kelvins. However, now we're talking about energy, and so we have to convert this number to joules. So these atmospheres and liters get converted over to joules to change this numerical number. So it's still a constant, it just has different units here. Because 1 joule is kilograms meters squared per second squared. And if we remember, here we have mass and velocity squared. That's kilograms meters per second squared. So we have to be able to relate it to that unit. So we've changed the units of R to be able to do that. Equating and solving, we get this equation here. The Avogadro's number times the mass is equal to the molar mass in kilograms per mole. So 3 times R as 8.31 times the temperature in kelvins. It's staying in kelvins. Avogadro's number times the mass, which is the same thing as 3 RT over the molar mass. As temperature increases, the average velocity increases. In order to have the same average kinetic energy, heavier molecules must have a slower average speed. So for instance, hydrogen is extremely fast. Notice how it's all the way out here in the velocity area, and it's only 2.02, whereas oxygen, out of all of these examples, is the heaviest at 32.0, and it is bunched up in the slowest regions. The absolute temperature increases, the average velocity increases. The distribution function spreads out, resulting in more molecules with faster speeds. Alright, so let's do one example of the RMS velocity. As we said before, RMS is equal to 3RT over M. Right here we have 25 degrees Celsius. That's easy to remember. We have to add 273 because it has to be in kelvins. So that becomes 298 kelvins. One difference with this molar mass here is that it has to be in kilograms per mole, not grams per mole. So they give us the molar mass is 16.04. We need to convert that to kilograms. So there's 1,000 grams and 1 kilogram. So that is equal to 0.01604 kilograms per mole. So let's take a look at our equation. 3. We're going to use that new 8.31 joules per mole Kelvin, because it has to be related to joules rather than atmospheres, times the temperature, 298. The kelvins cancel. 0.01604 kilograms per mole. The moles cancel. We're going to take the square root of all of that. That is going to equal 680 meters per second. So it sounds really complicated, but once you actually get to the point where you're doing the calculations, it gets a little easier. You essentially take 3 times 8.314 times the temperature in kelvins and divide it by the molar mass, but the molar mass has to be converted to kilograms. So you have to divide it by 1,000 before you can do it. And then take the square root. And that is explaining the kinetic molecular theory.